continuation of homework 13 is problem number 2. We have this crank slider, which is a mechanism. It's like a crankshaft, connecting rod, and piston that you'd find in an engine. The piston is usually in line with the same axis as the crankshaft, but that's okay. This is like an offset crank slider, I think they call it. And this has got the dimensions of 275 millimeters here and 475 millimeters. And at this instant shown, this thing is at 60 degrees and this one's at 45 degrees. And this crank is rotating at a 4 radians per second. So I call this a crank slider because the crank is driving the slider. Sometimes I might call it a slider crank if I were to know what this velocity was right here. Like, so if this one was driving it, I call it a slider crank. If this one drives, I call it a crank slider. But you don't care. All right. So anyway, here is what this looks like, my version of the thing. And we want to use this time we're going to find the velocity of C. But like in problem 1, we used vector math. This time we're going to use the 3-diagram method, and we're going to have other practice doing this. We need a lot more practice. We only have 2 homework problems, so we're going to have to get really good at vector math and really good at this 3-diagram method. In the next homework, we're actually going to do an additional method called instantaneous center rotation. So, and we're going to do the same problem so we can confirm the answers. Hopefully I get the right answer the first time, but we'll see. All right, so when we have multiple pieces right here, we only have 2 pieces. Don't really count that piston as a piece. We kind of march through, usually from the direction that we know, right? So what we know about this crank right here is it's like a fixed, pure rotation kind of piece. So I'll draw the thing out here. Just try to be neat. Yeah, I'm just going to approximate that. There we go. All right. So we want the velocity at B, knowing that it's moving right here. And it's moving this amount right here, this omega AB. Well, that velocity is going to be perpendicular to this right here. And we can find the velocity of B is simply going to be equal to omega AB times LAB, right? And so that's going to be 4. We were given it's 4 radians per second, and the length, we'll keep in millimeters, so 275. So we have 4 times 275, and that's 1,100 millimeters per second. Great. And we could do a little bit of geometry here. Kind of helps us out. We know that this is 60 degrees right here. 60 degrees. Didn't fit in there. The thing got in my way. How dare it. 60 degrees in there. And if that's 60 degrees, therefore that is 30 degrees, and that so make that this right here makes this 30 degrees, right? Because this right here is 60 degrees. I like to go from horizontal with things if I can, so that's the reason why I'm picking that. I could also say that I know that this is 60 degrees as well. Either way, okay. So that's going to give me the first thing that I need to know. The next, I'm going to do the 3-diagram method of this guy right here. So I'll use a lot of space. Come down here. And I don't need to draw him the same length, but I will kind of try to draw him the same length every time. You know what I could do is I could just draw a bunch of diagonal lines here and then erase them as I needed to. Yeah, there you go. And I'll erase this guy. I'm cheating. It's okay. Just want to make them neat. something like that. Oh, you didn't see it. Okay. All right, so equals plus. We're going to find the velocity by taking what we know plus a rotation. So for this one, this from here, we just found this to be right here in that direction. Right, so there is the velocity of B right there. And we happen to know that it's at, let's see, 30 degrees. All right, so one thing we do know about C is it has to be horizontal. So I don't know, I'm going to pretend like I don't know, but I could kind of guess which direction it's going to go. So it's going to go along this line. What I do, my method, right, I'm going to write underneath there, is that I want to find the velocity of C by equaling velocity of B plus the velocity of C with respect to B. Right? That's the equation that this diagram represents. So what I do here at C is I put, what I do over here for this guy at this location C is I place the velocity at that location. So here's the velocity of B, and I place it in velocity of B. Okay, so I've moved that to this spot, and then I pin it at the reference location, right? And now I'm going to treat this last guy like a pure rotation case, right? So I'm going to draw that like right there, right? So this is going to rotate, and we can pretend like we don't know which direction it's going to rotate. So I'm going to do that. I'm going to say that this is omega BC, right? That's this thing's rotation, and I'm choosing it as to be counterclockwise, which means that we're going to have the velocity of C with respect to B is going to be going that way because of that counterclockwise rotation. And we also happen to know, and this may be perhaps too easy because it's 45 degrees, but that's 45 degrees right there, because it's got to be, that's the arrangement, right? This thing is 45 degrees right there, so that has to be 45 degrees. It could be a little bit more complicated when we have, when we have other angles. We have to be a little bit more careful, but I chose sort of like an easy problem to start with. And oh, by the way, this guy is still 30 degrees. It's a good thing to write down right here. Okay. So we're going to write out the equation underneath this for the stuff that we know. I'm going to keep it that way. Okay. Velocity of C is going to be equal to velocity of B. I actually think I have enough with the vectors. All right, so what I want to do is I want to, the main idea of the 3 diagram is to focus in, like this equation is written for this point only. This was just to, that's the rest of the thing is happening up here. Here's the general motion, here's pure translation, right? They're both parallel, so this thing is just moving down that way right there, right? And then now we have pure rotation. Pure translation, pure rotation, add them together, are going to get the total here. So, but focusing in on this point right here, we're going to say that this is the final value plus the translational part of it, which we're using B because if it's known, it's our reference, and then the relative motion part right here. So we're going to put right in there. And so we go, and by the way, sometimes I like to write this over to the side. VC with respect to B is omega BC times L BC. Right? That's the magnitude of this. You can see there's no hat right there. So I want to use this, but I'm going to actually write out for that. Okay. So I write down in the x direction, and honestly, well, let me go back. All right, I'll go ahead and jump to some of the strategy that we have here. In the y, we start with the y direction. Why do we start with the y direction? Because it's 0 right here. That's my strategy. It's going to be equal to, now it's negative right here, right? It's going to have a negative component, a negative VB, which we know is 1,100, but now it's going to be the sine of 30 degrees. All right, so, and then we get over to this one, and we're going to see in the y direction, we're going to go plus omega BC times LBC, which is 475. But this is only going to be the sine of 45 right here, right? So that's the y component of this piece right here. Here's the downwards y component up here. Here's the upwards y component, and they're going to equal 0. So actually, we got the direction on accident. We got it correct because we know that's going to be negative and that's going to be positive to make that 0, right? So we can actually solve. So multiply 1,100 times the sine of 30, so 550, and then we're going to divide by 475 and divide by the sine of 45, and what we find is omega BC is going to be equal to 1.638 radians per second, and we note that we got correct that it was counterclockwise, so that's good. So now what we could do is we can go the x direction, and we have the entirety of VC, and I didn't choose what direction. I didn't even draw the arrow onto the thing. We could just write that VC is right there. We didn't know which way it's going to go. It's going to be equal to, all right, we have this one now, the horizontal component of that, which is going to be positive 1,100, and now the cosine of 30, and then plus now, okay, because we got this correct, so it is going this way, and so it's going to be omega BC times LBC, so we know omega BC is 1.638, and we know that this is 475, and now we want the cosine of 45, which I know. So we got a VC, and so I already have that in the calculator, so I'll go 475 times it, and 45 cosine times it, okay, ends up being 550, which you expected. 1,100 times the cosine of 30, boom, add them together, and you get 1,503 millimeters per second. So that's going to be the answer. And we know that it's positive, so it is going to the right. So there you go. VC is equal to 1,500 millimeters per second, given an arrow because it has a vector hat. We want the vector. If we want the velocity, if we ask for velocity, velocity is a vector, so you need to give it with a vector hat on, and that means it also needs a direction. But this is easy. So this problem is actually pretty easy, but it's a good one to start with. We're going to have to do these again and again because when we do acceleration analysis, we have to do a velocity analysis. So, and we're going to see sometimes this is going to be the easiest method. All right, so I did this in, let's see, what time is it? How much time did I use? 15 minutes, 14 minutes. All right, so here is the Solidworks simulation of this. And you can see, look at that answer right there, right at the top, 1503. Hey, I got the right thing. So this is what that this is what the motion looks like. You can see it reverses. And it looks to me like we accidentally somehow got the peak, right? It looks like we actually forming this thing at the beginning right here. You could see we could move, can see that that's going to be the maximum according to this right here. But I put on a motor onto this thing to give it a constant 4 radians per second answer. But you can see the velocity vector moving right in there. All right, so there you go. That is problem number 2, and we're done with the homework. Yay.